the sp2 hybrid has 1 part S and 2 parts P. So it's 1/3 S character, 2/3 P character. So these are 33 1/3% S and 66 2/3 percent P. 1 of 3, 33 1/3, 2 of 3, 66 2/3. So the sp2 hybrids are richer in S content than the sp3 hybrids. The sp2 hybrids are richer in S content than the sp3 hybrids. I would expect them then to be rounder, smaller, lower energy. We'll come back to that in a second. Okay, the last hydrocarbon that we are interested in is ethine, which is C triple bond C H. It's called ethine, formula C2H2. What are the features of this species that I want to account for? Clean the board a little. What are the features that I want to account for? Well, one is that the carbon is tetravalent. Two, that all, in this case both, CH bonds are identical. It turns out the molecule is linear. The molecule is linear. And there are also 2 types of carbon-carbon bonds. So the difference is this molecule is linear. Okay. Can we account for this? Well, I've got I've done this twice now. So I know the tetravalence requires that we have an excited state, right? So 1s2, 2s1, 2px1, 2py1, 2pz1, and in many practical ways, that's the launching pad for hybridization, right? What we're going to do now is mix 1 part S with 1 part P and make a hybridized state that is 2sp, 2sp, 2px, 2py1, 2pz1. 1 part S, 1 part P, sp, really s1, p1, but we don't write it once. 2 orbitals give 2 orbitals. Where are the electrons? Or when the S and the P overlap, when the atomic orbitals overlap to form the hybrid, these disappear, and I have 1 in each of those. So presto, 4 unpaired electrons. Tetravalence. But those 4 unpaired electrons, although the electrons are identical, the orbitals housing them are different. The sp hybrid is very round, very small, very low energy. We'll get to that in a little bit. So it means the electrons in the sp hybrid are very close to the carbon nucleus. Closer, in fact, than the ones in the sp2. They're very close to the carbon nucleus. Therefore, the repulsion between them is massive. Miles away are the electrons in the p orbitals. Those electrons in the p's are miles from each other and miles from the 2 in the sp hybrids. So the only ones that have shape determining properties, the only ones between which there is any kind of repulsion, are the electrons in the sp hybrids. So they determine the shape. And if I have 2 sites of meaningful electron repulsion, they will repel each other into a linear arrangement. So what do I get? I get a carbon with 2 sp hybrids. I get a carbon with 2 sp hybrids. each having one electron. A p orbital in this case the y axis, looks weird. And then another one coming out of the board and going back in. So I'll draw it like this. It's coming out of the board and going back in. Each of these has one electron. So it's an sp, sp, py, pz. There's another carbon with the sp hybrid and sp hybrid. P, Z, and PY, and then a PZ coming off the board and going back in. Right? Each having one electron. Now, see, and again, putting a dot here for the electron is absurd, because the electron is not a dot. The electron density fills the orbital, fills the entire loops. But for, just for the case of counting, I'm just going to put it as a dot. So what do I get? As you might imagine, these overlap end on or collinearly. This overlaps with a 1s of a hydrogen with one electron, collinearly. Same thing here. So what I'm going to get is a carbon-carbon sigma bond. I'm running out of space, I'm going to draw these a little bit smaller. Right? Carbon-carbon sigma bond, carbon-hydrogen sigma bonds, all in a straight line, 3 sigma bonds. And then I'll have the p orbitals like so. Okay? Each having one electron. Well, that's not good. The carbons don't have octets, right? 2, 4, 1 here 5, 1 here 6. 2, 4, 5, 6. To get an octet, I must have the p orbitals overlap. So they're going to overlap sideways here and here, here and in the back of the board. So I get one set overlapping this way, py, py, so top and bottom, and one set overlapping this way, pz, pz, front and back. But here's the problem. The p orbitals are not figure 8s. They're not two-dimensional. They are dumbbells. So as much as I can describe them as having shape this way, I can describe them having shape that way. So you can imagine then the py occupying a volume of space, not an area, but a volume of space like this and like this. The pz occupies a volume of space like this and like this. So what happens is, when the pz's overlap this way, because they have volume here, this overlaps with this part of the py. And that happens in front and in the back. So put it this way, imagine taking a balloon, taking four balloons, blowing up 2, and then 6, we're going to need 8. So we take 2 balloons, blow them up, and then tie the mouthpieces together. So I make a dumbbell. And I do that 3 other times. So I've got 4 dumbbells. If I take one dumbbell and I put the other one so that they're perpendicular, you can already see how there's contact between the one in the y direction and the one in the z direction. And if I take that system, that 4 balloons tied together, and touch them with another 4, everybody has contact. So the ones in front have contact here and here. The ones on top have contact here, here, and here. So in reality, what we get is a scenario in which these overlap here and here. This overlaps there and there. This overlaps here and here, and so on and so on and so on. So what you actually get is something that looks like this. There really now is a cylinder of charge, right? That is my pi system. I call it my pi system. So you can almost imagine the alkyne as having HCCH, like a pencil, inside of a soda can, right? And you can almost tilt the pencil around, right? So in many ways, it really is like a pencil inside of a can or something, a cylinder. Right, in fact, that's called a cylinder of charge. So I think got a cylinder of charge. And that really is also depicted as C triple bond H. So C triple bond CH. What does that account for? Tetravalence, 400 electrons. Both CH bonds are identical, of course they are. They form from the identical basis set of orbitals. sp, s, sp, and s. It's linear, of course it is. There are 2 sites of shape determining electron density. They control everything. They repel it into a straight line, the EPR theory. And the H is now simply inherited. So linear carbon, straight line. The H's come on the sides, straight linear compound. 2 types of carbon-carbon bonds. Yes, a sigma formed by the sp-sp overlap, sigma, and then there are pi's formed by pp overlap. So I've got a sigma, and one of these is sigma, the other is a pi. Remember we mentioned that. In any multiple bond, one is sigma, the other is a pi. So I can explain the bonding then of carbon in its hydrocarbons, which are important, and we see in all the compounds based upon hybridization. 2 things left to address. 1, how do I know which hybridization state to invoke? I mean, how do I know to pick sp3 or when to do sp2 or when to do sp? How do I know that? That's question 1. And question 2 is, now that we have a more comprehensive picture of the menu of the types of hybridization, what does that mean in terms of the energies and the look of the hybrids? So we start with that. So if you remember, we started drawing a diagram in which we had energy levels of my s and p orbitals. So this is a crude diagram. I'm going to say energy on this axis. Here is my 2s. That's the here's my 2s. Draw it like this. Here is my 2p. Here are my 2p's. I'm going to draw the 2p like this. Okay? If I break up this distance into quarters, so quarter, nice. Quarter. So this is 75. This is 100% P. Oh, yeah. This is energy. So percent S, percent P. This is 0% S, 100% P. And at the bottom here, this is 100% S, 0% P. So if I say that's a quarter, a half, 3/4, the sp3 hybrid, which is 25% S and 175% P, this is where the sp3 hybrids would be. Right? This is sp3. They would look more P-like than S-like. So the orbital, in fact, yeah, I'm going to slide this over so I have a room. So if I say this is P, so it looks like this. With the nucleus here, that's P. This is S. The sp3 will look rounder, maybe not quite that round, it will look rounder and smaller than the P orbital. So you notice it's not quite as long, it's not quite as dumbbelly shaped, it's a bit more round than this one. And it's starting to lose this tail. If I divide the gap into thirds instead, then you kind of see where this is going. So 1/3, well, 2/3, then this would be 33⅓% S and 66⅔% P. This is where the 3 sp2 hybrids would reside. They will be rounder than this, and I'm beginning to lose even more of my vestigial tail. It's rounder and smaller, right? It's rounder and smaller than that one. If I divide the gap in half for SP, right, that's about here, I've got 50% S, 50% P, and they're 2 SP hybrids. And they will look, they're smaller and even rounder. So that's my SP. I'll have to adjust this down a little bit. So the S would be like that. So what you see then, this is the nucleus. What you see then is that as we go from P to S, the size of the orbital contracts, it gets progressively rounder, and its energy content goes down. Okay? Any textbook you have for organic will give you a much better diagram than that. That's kind of a crude approximation. Okay, the last thing we talk about, and we will pick it up in some more detail later on, is how can I tell the hybridization state, when to pick which hybridization state. So let's imagine I have this compound. Suppose I were to ask you, what are the hybridization states of each of the carbons in that compound? So how do we do that? Well, I know that all pi bonds require pp side-on overlap. All pi bonds are specific in terms of who overlaps, they must be p, and how they overlap, must be side-on. Contrast that with sigma, who doesn't care who you are, as long as you overlap end-on. So I have to ask, when I look at a molecule, and I'm asked about hybridization state, how many pi bonds are you forming? Because remember, your basis set is always here. This is where you start off. This is your launching pad for hybridization, right? The system excites, right? It excites into 2s1, 2bx1, 2by1, 2bz1, and then waits for further instructions. If the instruction is form no pi bonds, only single bonds, well then I don't need p orbitals. P orbitals are only needed to form pi bonds. So I'm going to hybridize the s with all the available p's. And I will be sp3 hybridized. So these carbons that are forming only single bonds, no pi bonds, are sp3 hybridized. What about that carbon? Well, that carbon is engaged in a pi bond. How many of them? One. So for this carbon to do its share of a pi bond, it needs to have one p orbital that is untouched, that is unhybridized. Because I must have to make the pi bond, it must be a p overlap. So this carbon must provide one p. Okay, good. So starting from my launching pad, I will reserve this p orbital for the necessary pi bond. I will hybridize the rest. And this will be sp2 hybridized. The same is true for that carbon. What about that carbon? How many pi bonds is it forming? Well, there's a triple bond in which one is sigma, the other is a pi. So you're forming two pi bonds. I need two pure p orbitals. So I'm going to start my launching pad. I'm going to reserve two p orbitals, leave them out, I'll hybridize the rest. So these will be sp hybridized. How many pi bonds does that carbon form? None. In which case, I don't need p orbitals. I'm going to hybridize everybody, and I'll be sp3 hybridized. So I can tell from the structure of the carbon and the number of pi bonds, if any, that it forms, what my hybridization state is. Right? It's all based upon the question, how many pi bonds do you form? And quite simply, right, number of pi's, of pi bonds, number of p's reserved, number of p's used, hybridization state. Number of pi bonds it forms? None. None. How many do I need to reserve? None. How many did I use? No p's reserved. Number available then, so number of p's available, better word. 3, so I'm going to be sp3. If I am forming one pi bond, I'm going to reserve one p. There'll be 2 available, so I'll be sp2. If I form 2 pi bonds, I'll need to reserve 2 p orbitals. I'll have 1 available, because there are only 3, so I'll be sp. You understand? sp1. Okay? And by the way, I can use 2 pi bonds either to the same atom or to different atoms. Right? So like in carbon dioxide, for example. This carbon is still forming 2 p orbital, 2 pi bonds. So this is also sp hybridized. Okay? Last point, and then we stop. Why do I hybridize? So I understand hybridization explaining the properties and the bonding in methane, ethene, ethyne. Okay? And that is enough. But from a more fundamental perspective, why do the atoms hybridize to begin with? I mean, what do I gain by hybridizing? Let's take methane. Suppose methane decided to bond this way. Well, what I would get is one bond that is short and strong and 3 long weak bonds. Now remember how we define bond energy. It was my Morse. What does a strong bond mean? A strong bond means it doesn't break easily. I've got to put a lot of energy in to break it. That's what a strong bond is. But it also means that a lot of energy is lost in its formation. So the stronger the bond, the more stable is the system. Right? So I prefer to have 3, it's better to form 4 medium strength bonds by forming bonds that are using sp3 hybrids, right? sp3, 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 sp3. If those overlap with S of the hydrogen, I will form 4 bonds of medium strength. That is a lot better than 1 strong bond and 3 pitifully weak bonds. So it is the carbon's advantage to hybridize, because that way you release more energy in the bonds that are formed. 4 medium bonds are better than 1 strong and 3 weak. Okay? Plus, if you look at the orbitals, the hybrids are progressively more stable than the P's. And again, it's a question of maintaining stability. This is not a good place from which to bond, because your orbitals are not particularly stable. Right? So it is to the atom's advantage to bond. The other thing is, if you look at carbon, remember we said that if carbon bonded that way in methane, you would form 3 bonds between the P and the S's that were perpendicular to each other, or orthogonal. But if you did that, the bond angles would be 90. And you would place your electron pairs at a closer solid angle, 90 degrees, than what you get when you're sp3 hybridized, which is 109.5. So that we minimize repulsion, right, when you sp3 hybridized. So hybridization is to your benefit. Okay? Here's my phone call. So thank you guys very much. Hello, Ron Darbo speaking. Hey, John.